These slides introduce species concepts, the ways in which we define and recognize species, both today and in the fossil record, as well as providing a very brief introduction to some of the procedures and rules of classification and nomenclature of species and other taxonomic groups. What is a species? Well, intuitively it seems fairly straightforward. We can all kind of recognize one when we see one, even if the differences can be quite subtle. In the case of, say, these birds down here, which look identical, but can be distinguished in other ways, by their calls, for example. But in reality, the answer to the question, what is a species, is much more complicated than you might have thought, and it's very difficult to come up with a definition that can really distinguish species. One widely used idea is the biological species concept, defined as a group of individuals that actually or potentially interbreed in nature. And the fundamental basis for this is that different species require reproductive isolation. That can occur because they physically are unable to mate, or they live in different places. It may be because they physically mate but cannot produce offspring, or it may even be that they can produce offspring, but those offspring themselves are not fertile. But the biological species concept has some issues. Most importantly, it's very impossible to apply to fossils, as we'll come back to. But there are problems. So what do we mean by potentially interbreeding? Many things can potentially interbreed, but don't because they live in different places of the world, for example. And there are many, many examples of things that we consider to be different species that can interbreed, like all of these llamas and so forth from South America. They all interbreed with each other. Whales and dolphins can interbreed, lions and tigers, and so forth. So clearly 100% reproductive isolation is not required. There are other issues of this interbreeding where, for example, with these salamanders in California, they occur in this ring around the Central Valley, and as you go from, say, Santa Barbara to San Francisco, up the coast, they can all interbreed. All these different groups can interbreed. And they can all interbreed with each other down the Sierras, but at the south end of the Sierras, right north of Los Angeles, where those two ends of the ring meet, those two groups cannot interbreed. So can they interbreed or can they not interbreed? Is this a species or is it many species? It's pretty ambiguous. Well, the whole point is kind of moot for our purposes because interbreeding is impossible to determine in fossil species in virtually all cases. So we have to use a species concept based just on morphology, and often just based on the morphology of the fossilized hard parts. So this is called the phenetic species concept. It's a set of individuals that can be separated morphologically from some other set of individuals. But this is fundamentally subjective. Two different people looking at groups of fossils might group them and divide them in different ways, because it really depends on what variations we consider to be important between species and what degree of variation we think is acceptable within a species. Because all species, as you probably know, just by looking at other humans, have variation in certain morphological features. So it becomes pretty subjective to divide groups based on simply on morphology. So the assumption of the phenetic species concept is that morphological differences reflect differences in the genetics and differences in the interbreeding and the evolutionary relationships of these groups. And in many cases that is likely going to be true. But we have to recognize that there are probably species that are different that we can't recognize on morphology, and there could be species that we think are different but are really not because of other factors. So we'll come back to that after we take a small divergence into the rules of classification. Organisms are classified using a Linnaean classification, named because it was invented by Linnaeus back in the 1700s. And Linnaean classification is a ranked classification scheme. There are different levels or ranks, such as the phylum and the class and the order. It's also a hierarchical classification scheme because those ranks contain other ranks within them. So a phylum can contain several classes, a class can contain several orders, and so forth. So the more inclusive groups, such as a species, are nested within the less inclusive groups, such as a genus. So in this classification, an important thing to point out is that a species should be a real biological entity. It should be a group of interbreeding organisms or organisms that shared a single common ancestor, or however we define a species. We hope that it's a real thing, biologically speaking, but all the levels above that are simply made up by us for convenience. They're artificial constructs that we use to organize our ideas of the diversity of life. Despite that, or that being said, we would hope that these higher taxonomic levels at least contain things that shared a common ancestor. We would not like our family, however we define it, to include a whole bunch of unrelated things. We would hope that all the things in that family have some sort of relationship to each other, evolutionary relationship. This Linnaean system, as we describe a species, is typological, and that means that everything has a definition based on individual types. So a species will have a type specimen chosen because we think it is most representative of the morphology of that species. And a genus will have a type species because we consider that that species is most representative of the genus. What this means is when you have a group of specimens and you want to determine whether it belongs to one species or the other, you should compare your specimens to the type specimen of that species and determine if you think that any morphological differences are significant enough to make it a different species, or if you think that the morphological differences can fall within the range of variability of a single species. This is that subjectivity that we get with morphological species descriptions. But the typological approach can have shortcomings too, especially if it's applied very strictly, as has been done in the past. Remember that species often have intraspecific or within-species variation. These ammonites in the pictures on the right here all are considered to belong to one species, but you can see there's quite a lot of variability in the shape of the coiling, in the strength of the ridges on the shells, and so forth. But the key point is that these are considered to be one species because there is a relatively continuous sequence of this variation from smooth to weakly ridged to strongly ridged shells, and measurements that we can make tend to fall in a bell curve type shape or normal distribution. Many things are kind of average and there are a few things towards the extreme. So that's what we can look for to see if the variability that we see is potentially one species or more than one species. But that's not the only aspect of variability that we might expect within a species. Species can also change shape as they grow from a juvenile to an adult. Ontogeny is the word that we give for the growth of an individual from its birth to when it reaches its adult shape, and any sort of shape changes that can happen. And these might be considerable. In this trilobite here, so these are pictures of the cephalon or the head region of the trilobite, and you can see that in the juvenile in the upper left, it's very circular, the cephalon. It's got these little spines that are sticking out the bottom, but as it grows, the head becomes progressively wider and wider. Those spines largely disappear. There are other shape changes as well, which you can probably note. So you have really to consider when looking at a species that you're not comparing juveniles and adults that might look different. They may not be two different species. They just might be juveniles and adults. But that's not even the final problem that we might have. One other issue to deal with is something called sexual dimorphism. And that simply is the idea that males and females might look different in some ways. It's most often recognized in ammonites, at least in terms of fossils, or fossil invertebrates. where there's a macroconch interpreted as the female and a microconch, typically smaller, interpreted as the male. As you might guess, this is pretty difficult to recognize in fossils unless you have a lot of specimens. There are ways that you can recognize this, and in class, what we're going to work on are exercises where you will look at specimens and measurements and try and determine how best to divide them into species, considering sexual dimorphism, considering how you can recognize that, ontogeny, and simply intraspecific variability.